think about and talk to each other, what is a regression model, and why do we, or how do we use that? Talk to each other, please. Actually,
how does it, what is it something? That's your life. It's a regression model.
Maybe if we go out with newspaper.
all right, ladies and gentlemen, figure out who your reporters are for the day. We'll hear from our reporters.
I'm definitely.
I'm a character. I'm a facilitator.
All right, reporters on your feet, please, so we can hear what you might think about regression models. I'll say it one more time. Thank you, Isaiah. Please, reporters on your feet, so we can hear your All right, please be respectful to our sharers, please. Thank you. All right, Michaela, help us out. What did you talk about regression?
We said a regression model is a scatter plot, and we use it when data is not always equal.
All right, thank you. Mr. Harmon?
We said it's a line of best fit, and because you use it because you can't find the right thing.
Okay. What did you guys say? You said line of best fit? Okay. To try to find what? Okay. Mr. Garcia?
Trying to connect on the points of the line.
Okay, so try to connect the points to the line of best fit, and did you want to add anything else? Okay. So the line of best fit we use, it might look something like that. Okay, so I like that we know when to use it. Michaela said we use it in the scatter plot. You guys are understanding the idea that we need to use a line of best fit. But when I say model, how are we modeling it? On a graph with a what? That's my question. What is the model?
It's a line on the.
Okay, it's the line, but what do we use to help us with that? It's the equation, okay? So the model is the equation of the line of best fit. And now we have to figure out, well, why do we use that? How does a line of best fit help us in a situation where we have this scatter plot? What's it going to do for us?
Maybe it's more
Okay. Because do any of those points really make sense? Are they in a definite pattern? No, they're not. But that line is in a definite pattern. So what does that help me do? Yes.
It helps you find the y-intercept, which you need to do the equation. Wait, no.
Maybe. I mean, helps me. I'll definitely need the y-intercept. What if this is my real work document here, and I have all these points, right? I'm in sales. I'm trying to figure out how much money I'm going to make after when the temperature is a certain amount of money. Can I use this scatter plot to help figure out what my sales will be when the temperature is 90 degrees? Why can't I? What's wrong with this graph? Okay? It doesn't go all the way up to 90. So if I have the equation, what can I do? Plug it in, and then I can make predictions about what's coming next. Okay? So you guys are going to work with regression. But here's the question though, because are we in a linear model or linear unit right now? What are we in? We're in exponential. Okay, so we're gonna, can anybody make predictions about what we might do today?
No.
Exponential regression models. Before you guys kick into this, I want to ask you a question. Let's go back in time. Who remembers what it was that we called something that like helped us determine how linear something was? Correlation, coefficient. What letter did we use for that? The R value. And somebody talk to us about how was that R helpful? What did it allow us to do? What did that number help us figure out? All right, so there's a positive or negative. Go ahead, Asia.
like if it was closer to 1, it would tell us. If it was more like close to linear, and if it was close to 0, it was like all over the
Yeah, all over the place, right? What happened? You have to keep on.
If it if you use whole values or decimals, I'm probably gonna use decimals.
Yeah, that was domain.
Yeah.
Want to answer the Caitlin? But Asia was really on target when she said, remember, the closer it is to 1, the stronger the relationship is, right? So that's what we're going to look at today. So here's your instructions on what you're going to do next. You guys are going to work with one other person. So whoever your shoulder partner is, that's who you're working with. You guys, maybe you guys want to work together, you guys work together, and you guys, we were already making the arrangements, who's working together. So you're going to have one computer between 2 people. So figure out whose computer are you using. Turn your desks now so that you can work together. Okay? One person's computer is being used. I can get that for you. All right, let's go. Get Blue's computer. Let's get it open. I want to have a conversation about some of the things that you guys talked about. So, am I frozen still? So originally, you guys all said, it looks like everybody's saying that it's an exponential function. There's not one kid in here who said linear. It starts off slow and increases quickly. There's not a constant rate of change. It's exponential because it doesn't go in a straight line. It's increasing at an increasing rate. And that's really nice that you guys were all able to utilize the ideas of what exponential functions look like to kind of predict that exponential would be a better model here. And then you went through and you did all these problems where you figured out what the linear model would be, what the exponential model would be. And by the time we get here, you guys did a nice job of writing the equations. You can see that all of your equations overlap the actual regression model. So you did a great job writing those equations. And I can't, unfortunately, see what your responses were here. But which one do you guys think was, even after doing all of this, do we still think is a better model? Do you still think that exponential is a better model? How could you prove it mathematically? Because I think it's pretty obvious, but how could you prove it mathematically? Did anybody answer that question? Like, what could you look at? Okay, so it is. It's absolutely, you're absolutely right. It's hitting more points. It's going through more points, definitely. But what would be a math that you're, and that's good. It's an obvious thing, but what else could we use to double check to make sure that we're right here? Not sure? Which one is stronger? Which one has a stronger relationship with the points? Okay, and I use the word stronger because I'm trying to get you to figure out what are we trying to, what's something we can always look at.
Which point?
The what?
Correlation.
The correlation coefficient. So I'm going to open this back up, and I want you guys to go back to slide 2. Go back to slide 2, and find out what are the R values for each of those regression models. And then did we make the best choice using an educated guess? So I need a linear R value, and I need an exponential R value. Maddie, what's the linear R value?
The linear is 0.72.
And what was the exponential model? 0.98. Did you guys make a good decision? Jeremiah, how does this confirm that exponential is the best model here?
Because it's a strong positive correlation.
Closer to what number?
Closer to 1.
Closer to 1, which would be a perfect fit. So this is nearly perfectly exponential. Make sense? All right. So I want you guys to start thinking about that R value and how really important it will be, especially in the next case, which might not be so obvious. So off you go. Slide over to slide number 5. And work with your partner to figure out what this situation might bring us. I got frozen. You should be able to go.
Yeah, but we have to finish that.
Oh, that's because I have to pace it. Sorry, my bad. Stop pacing. My bad. Off you go. Thank you. Ooh. Uh-oh. Is this scatter plot quite as obvious as the other one?
No.
Not even close. Alright, so we're gonna have to do maybe a little educated guess here, or maybe just a guesstimate.
I think
Linear
What do you guys think? I'm gonna think linear, why? Okay, so we're heading over there.
Oh my God.
Linear, what do you guys think?
Going upwards.
So looking at where I used to learn from, so I said, is that weird?
And 3, thank you. All right, so I paused the activity so we could have a little bit of a conversation. What was different about this scatter plot compared to the first scatter plot that we looked at? Yes,
X value?
say that again?
X value?
What do you mean?
Whether plug in the actual number in the.
I meant like the scatter plot, like the first slide of each new problem. How was one different from the other? Yes.
The points are more together.
The what?
The points are more together.
What do you mean by that, more together?
They were more going in one direction.
Yeah, they were more following an obvious pattern, right? When you guys got to this problem in slide number 6 and saw what those points were, I heard a couple of, or actually slide 5, I heard a couple of uh-ohs because it's not obvious, right? It's not obvious at all. And it might have been more, like, I think as I walked around, almost all of you said it was linear. And somebody talked to me about why you, just by looking at it, really kind of pushed more towards the linear side, even though it's not specifically obvious. Michaela?
More dots are going in a straight line.
All right, so you're maybe looking at these guys here, these 3 here, maybe thinking that you could draw some kind of straight line. It's not a bad theory to think that that might be the way to go here. And then as you guys did your regression models, we came up with regression models that look like this, that kind of passed through the data. And here's where Michaela's, she's looking 1, 2, it goes through 2 points. And whereas the exponential, it only goes through 1. So maybe that's a deciding factor. Jeremiah, you guys talked about originally, right, that you thought after you did this whole activity that the exponential model was best.
Yes.
Can you talk to us about why you thought that? Because you're in the vast minority.
Because the exponential line went through the actual point, but then later we actually found that the correlation, the linear correlation coefficient was actually slightly stronger than the exponential one, so altogether it's actually linear and it's better.
Yeah, so you had one opinion, but then when you chose that mathematical calculation to check your understanding, it was slightly in the other direction. And I'm with you, like, I might have thought that this was a little bit more exponential than the others, but that correlation coefficient is by far the best determining factor there. So things that you guys said about what we could check for if it's really close. Somebody said depending on the numbers in the equation, we can figure out which model is better. Is it the numbers in the equation that help you determine what's better, Connor? No, so it's not the numbers in the equation. What do we think about this one? Can you guys take a look and read this one up here? Mr. Harmon, can you read this? By using the correlation coefficient in the problem. What does that mean? Do you think that this is a good explanation here?
Yes.
Why?
Because you make the correlation coefficient.
What does it help you do?
You use how to
Okay, so in this case, the correlation they say here is 0.81. I love this example because they gave you the 2 correlation coefficients. That's a really nice supportive answer here. So again, the correlation coefficient. In this case, they didn't use that idea here. Correlation coefficient is slightly stronger in comparison with the exponential correlation coefficient, so the linear would be the best. So this is, I love, this is awesome. So again, the correlation coefficient. So again, talk with your group members. What should be the ultimate deciding factor on how you determine what is the best fit? Talk to your group members. I'm so glad that you had that happen. All right, questions or comments, ladies and gentlemen? Are we all good with the idea of the correlation coefficient being that big idea that we have to use to help us determine? All right, fantastic. All right, here's the next thing we're going to do. We are all going to open up our computers. Everyone's working individually.